Hi, I have a question about the Level 3 2018 electricity paper, and the specific question was question 2C. And so I'll just go straight on to question 2C. It's question 2. So this is about, so I just won't work through one because you know that. So this is about an inductor which has a resistance. So it's shown as 1 unit. It's connected to a 12-volt DC battery with a 0.0900 ohm internal resistance. And then if I just scroll down. Okay, so to prevent, so when she opens the switch, if this wasn't there, there'd be a spark. So to prevent sparks, she has this resistor in parallel with the electromagnet. And the question is, at one point, shortly after the switch is closed, the current from the battery has reached 2 amps and the back EMF is 9 volts. So that means the EMF across that is 9 volts. Show that the current through the electromagnet is 1.41 amps. So if you look at this, so when the switch is closed, this is essentially a parallel circuit, and this is like your year 12 one. So the voltage across every branch is the same. Now that's a supply voltage, 12 volts, but some of the energy is used up by the internal resistance. So voltage lost across internal resistance is the circuit current times internal resistance, which is 0.18 volts. And so the voltage available to the rest of the circuit or across each branch is 12 minus 0.18 volts, which is 11.82 volts. So that whole bottom branch has got 11.82 volts, but the voltage across the inductance is 9 volts. So the voltage across the resistance is 11.82 minus 9, so which is 2.82 volts. Now the current in any branch is determined by the voltage across the resistor and divided by the resistance. So 2.82 divided by the resistance is 2 over here. That's how you get the 1.41 amps. Okay, now going further, this next part, this is where you want it. So after many more minutes, the current is steady at 5.72 amps. That means there's no voltage across the inductor. The switch is opened, and plot the graph of current versus time as the current falls to 0. So the first thing you need to know is the time constant. So the time constant, so what actually happens is when the switch is opened, this inductor is going to discharge through this resistor. Okay, and so the time constant is L divided by R. So this is essentially now a series circuit. So the total resistance is 20 plus 2, 22. Okay, so you go L over R, and then you get, so that's your time constant, 0.45. That's 4.5 times 10 to the power of -1 is 0.45 divided by 22. You get 0.020 seconds. So each of these is one time constant. And then, so after one, so it's a decay curve. And how do you calculate what's the current after 1 time constant, 2 time constant, 3 time constant? So the formula is maximum current 5.72 E -1, you get 2.10 amps after 1 time constant. After 2 time constant, it drops further to 0.077. After 3 time constants, you just do 5.72 E -1, and you end up with 0.28 amps. So all that you do, I don't know if I can plot points, I may not be able to. So this is 5.72 is like somewhere here, let's say. Okay, not exact, but you get the idea. Make it smaller. And that's probably as much as I can get. Okay, and then after 1 time constant, it's 2.10, so it's somewhere over here. After 3, it's after 1 time constant, and then after 2 time constant, it is 0.77, so it's somewhere over here. And then after 3 time constant, it's 0.28, somewhere over here, and so on. And then you just, I can't draw a line, but you kind of trace it for you. So that's the sort of decay curve you get. And then the next one is, how does the presence of the 2 ohm resistor protect against high voltage sparks? So the thing is, if I just look at this here, so when she's discharged, when the switch is open and there's a resistor, so this